This mini lecture is about control systems. Early on in the course, I mentioned how control systems are important for maintaining a constant internal environment within the body. And a statement I made early on was that physiology is dynamic. It allows you to run and leap and do all kinds of dynamic things, behaviors, etc. But of course, the cells and the molecules within those cells are fragile in the body. So that's the challenge for these control systems, to maintain homeostasis, a constant internal state, against the changes in environment and activity that you may impose on that physiology. So that is resolved by control systems, physiological control systems. And in order to consider those control systems, we're going to start talking about the nervous system on a broader scale, not just individual neurons, but how the nervous system works in conjunction with physiological systems in order to facilitate homeostasis. Now, before we get into the specifics of how your physiology does that, we want to establish some basic intuition for how control systems work at all. So the question for this mini lecture is, what kind of control generates homeostasis? And we're going to contrast that kind of control with a couple of alternatives. So we're largely going to be talking here about control systems pretty abstractly for this lecture, but then in future lectures, it's really a theme that's going to pervade all the rest of this course. We'll talk about the physiology. Okay, so starting with a non-physiological example, a thermostat. And a thermostat illustrates negative feedback, which is a form of control. So here's an old school thermostat, which has two readings of temperature, two displays of temperature. One is the current temperature, so think of that as a thermometer. And in control language, which we need to introduce, we would call temperature here our state variable. Our state variable is the measure that our control system cares about. It's what is being controlled. And so that's temperature in this case. And the thermostat itself is making computations in order to control a furnace that serves to maintain the temperature around a comfortable target. And that target is known as the set point. So that's what you dial in on the thermostat. That's your desired temperature in this case. But of course, we're just using temperature as an illustration for control in general. Set point, state variable, and integrating center are all generic terms that we would apply to a variety of physiological control systems. This old school thermometer works mechanically. It has a mercury switch on its interior. It has a temperature sensitive coil. It all works mechanically, so the behavior that I'm going to describe is really a mechanical phenomenon. Of course, this is all done digitally with electronics these days. All right, so how does our state variable of temperature change over time? We're going to consider a scenario where you're in a really cold house, and you dial in the thermostat to turn on the heat so that you get to a more comfortable temperature. The goal is to maintain the temperature around a desirable set point as best possible. So we start off with that really cold temperature, 0 degrees C. And we walk into this house and we set our set point on that dial on the left to 35 degrees Celsius. Here it's shown as Fahrenheit. We're going to dial in a Celsius temperature. The furnace will kick on in response to that. The heat that it generates will elevate the temperature, of course. And at a certain point, we exceed the set point. So here we've got the set point as the horizontal line. We can see that the temperature goes above that. That's intentional. That's in the nature of our controller. But we don't want to go too high because, of course, our goal is to stay at the set point. So the furnace will turn off, and then the building will start to cool. The temperature will therefore drop until it goes low enough to re-trigger the thermostat and thereby turn the furnace back on again, like that. Okay, that heats it up, and then we have these oscillations through time. So our control system doesn't do a perfect job of keeping our state variable at the set point. There's oscillations around that. That's typical for control systems. So some control systems are have very narrow tolerances and are capable of maintaining variation around that set point over a very narrow range. And other control systems are sloppier and allow for these oscillations. Okay, now we need to introduce some more jargon and some concepts here to really understand what's going on. First of all, the difference between the temperature, our state variable, and our set point, which we're denoting with the letter P, that difference is critical to how a control system works. Initially, we're really far away from our set point, and so the difference between S and P indicates how well the controller is doing at any point in time. We call that difference the error. It's telling us, you can think of it as just like how poorly our state variable is relative to our set point. Now I mentioned that the furnace turns on, it overshoots the set point, and then it eventually turns off. That overshoot occurs up to some measure of the error. And that difference is known as a high threshold, or the letter tau. So you can think of tau as being a particular value. So that's the letter tau. You can think of tau, which is shown by the height of that arrow. It's the error value at which something happens. So in this case, the furnace turns off when the error reaches that high threshold. Then again, as the temperature drops and the furnace turns back on, which occurs right there and drives the temperature to increase again, that occurs at another threshold. That's the low threshold. And in the simplest case, the high threshold is just the inverse of the low threshold. So we're going to denote the low threshold as negative tau. It's the error value that occurs when the furnace turns on. So now that we have these quantitative concepts, we can articulate what the thermostat is doing in terms of a set of rules. And there's two rules in this case. The first rule has to do with turning the furnace on. And that rule is like this. If the error, the difference between the state variable and the set point, is less than the lower threshold, minus tau, then turn the furnace on. So if the furnace was off, turn it on. If it's already on, you leave it on. But this rule has to do with changing the state of the furnace off to on. The second rule has to do with what occurs at the high threshold. And there, if the error exceeds the high threshold of tau, then turn the furnace off. Now that first rule of what occurs relative to the low threshold, let me change my pointer here. That first rule occurs here because we are below that low threshold. And then it occurs again right there. And the reason why it looks different is just that we were starting off at such a low temperature value. And here it just peaks a little bit below the lower threshold in order to trigger the same rule. So this rule here applies both to this event where the furnace initially turns on and then the second turning on of the furnace. The same rule works for both instances. And then eventually, as this temperature would rise, then the second rule would apply because we would exceed the high threshold. So we've got two rules. Together, they allow us to formulate an algorithm. So control systems need a set of instructions, how to respond, in this case, to a temperature measurement with either turning the furnace on or turning it off. So we can represent control systems as flowcharts. And in the center of these flowcharts, or in this case at the top of the flowchart, we have our integrating center. That's the thermostat. Now as an output, we have the furnace. That's an action that is recruited by the integrating center. And that furnace has an effect on the state variable. The state variable is monitored by the thermometer within the thermostat, or a temperature sensor. Now we're beginning to see why there's a feedback in the term negative feedback, because the temperature sensor is compared against a set point, in this case 35 degrees Celsius. The difference between those two quantities gives us our error, and it's the error that the integrating center does something with in determining how the furnace should be controlled. The furnace is an example of what we call something along an efferent pathway. Efferent pathways with an E have an effect on the state variable. The temperature sensor, on the other hand, is with an an example of something along an afferent pathway. Afferent pathways are sensory. Efferent pathways are actions that influence the state variable. The temperatures, the sensing of temperature by that thermometer illustrates feedback. And it sets up a situation where the efferent response and the influence on the state variable is detected by the afferent pathway. In other words, the afferent pathway influences or modulates the efferent response. So this is a control loop. The furnace heats up the room. That affects the temperature. It's detected by the sensor. The difference between the set point and the reported temperature are considered by the integrating center, and then it decides whether or not to change the state of the furnace from off to on or on to off according to these rules. So it's the algorithm feeding into the integrating center that determines the actions along the efferent pathway. So we can say that a negative feedback loop acts to maintain a state variable around a set point. Okay, again, it's not perfect, but by virtue of these actions by the controller, we're maintaining temperature around the set point. So negative feedback loops are the kinds of control systems that facilitate homeostasis. If it's a system where something is regulated, we're talking about temperature regulation, blood pressure regulation, regulation of ion balance in the body, regulation of sex hormones. Whatever it is, if it is the term regulation, then that suggests a negative feedback loop and a negative feedback controller. Now we can contrast negative feedback with positive feedback. All right, a lot of the same parts still apply. We've got two notable differences here. First of all, there is the threshold. Okay, this actually should be tau, not p, because it's the difference between a threshold and the state variable that determines the actions by the integrating center. Okay, in this case, the threshold is a little bit different. It's not defined as a particular value of the error, but instead it's a particular value of the state variable itself. Now, the algorithm is where things are really different. The algorithm says there's two rules. The first one says if the state variable exceeds the threshold, in other words, if the difference between s, the state variable, and tau, the threshold, is greater than 0, then activate our efferent pathway. Turn it on. In this case, we're going to turn on the furnace. Now, this furnace is different from the one that we consider for the negative feedback loop because it has a variable intensity. We're going to call that the furnace level. It can run at low, medium, high, and very high levels. And the level that the furnace runs at is proportional to the state variable itself. So let's consider how that works. First of all, let's say that the temperature rises above the threshold. This would require some action in order to turn it on. So let's just say in this scenario, we turn it on low. Then it reaches the threshold. Okay, so now we've turned the furnace on. The first rule has been satisfied. Now we're in a situation where the efferent pathway depends on the state variable. So the level of the furnace is now being dictated by the temperature as read by the temperature sensor. So as the temperature goes up, that is then going to drive the furnace to run at a higher level. So now we're at level medium. That rise in temperature, in turn, drives the integrating center to turn the furnace up even more. So the furnace is now at a high level. And this would just keep on going until our state variable approaches infinity. Okay, it goes up and up and up. Of course, this is not possible. Eventually, the furnace would burn out. It has a maximum level that it can operate at. And so there is the need for an external shutoff of some sort to prevent this from going to infinity. But what this illustrates is the characteristic curve, an exponential rise that is characteristic of positive feedback loops. So even though the flow chart looks vaguely similar to a negative feedback loop, if our efferent output is proportional or a function of the state variable, then you've created a situation for positive feedback. The third type of control is a feed-forward controller. Okay, so here we've got the correct tau. Again, there's a threshold. That's what's going to turn on our system. And we can see that here. If we exceed the threshold, then we turn on. But so let's see how that plays out over time. We turn the furnace on and the temperature rises. And we have it rising if the furnace is on low or if it's on high. But it's at a fixed level and the temperature just goes up over time. The key distinction between feed-forward control and the other two controllers that we've mentioned is that there is actually no feedback. The temperature is monitored only in order to initiate the efferent response. Once initiated, then that efferent response no longer depends on the afferent pathway. So there is no feedback in a feed-forward control system. The efferent output is independent of the afferent input. The afferent input is useful just to initiate a feed-forward controller, After it has initiated, then it just plays out in a very consistent way. So let me summarize. We have the feed-forward control that I just described. It's relatively simple. You don't have a feedback loop. And feed-forward controllers tend to be fast-acting. They're just playing out a pattern on the efferent side, and it's not modulated. So we'll see examples of this when we consider reflex arcs, such as in the musculoskeletal system, and autonomic reflex arcs. We've considered negative feedback. These are more complicated because of a feedback loop, but they offer a modulated response. And so this is good for regulatory functions. This will achieve homeostasis. Positive feedback loops have the same essential parts as a negative feedback loop, but they have a very rapid rise that is exponential. And by virtue of being exponential, it quite quickly sort of moves out of control. And so that requires some sort of external shutoff. In our example of the furnace would have to fail or reach its maximum. In the case, we've actually considered a positive feedback loop example, which is the sodium voltage-gated channels that drive an action potential. So when the cell membrane is depolarizing on the rise of an action potential, it has exponential growth like this. But the inactivation gate in the voltage-gated channels shut off the system. Now, positive feedback loops are no good for homeostasis, but they are beneficial for very rapid action. So we're going to see very few examples of them as we consider physiological systems. Homeostasis is generated by negative feedback control. So most of the control systems that we'll talk about focus on negative feedback, but we'll see some examples of the other two as well.